Hello again, everyone, and welcome back to another Fluence Tech Talk. I'm Jason Bowman, and today we're here to discuss high-rate anaerobic systems, the when, the where, and the why these systems make sense. I'll provide a general overview of high-rate digestion and then focus more specifically on our EFC process. So thanks for joining, and I hope you enjoy. Okay, so let's get started. If you followed along to previous tech talks or even our webinars, then you've probably heard me discuss the different anaerobic digester project models. Anaerobic systems are often associated with high solids treatment, where the primary objective of these project models is to gain as much sludge and solids content, organic content, to maximize biogas output. Today, however, our focus will be utilizing digesters as the core wastewater pretreatment process for industrial applications. So the role of these anaerobic systems shifts from maximizing biogas output to process optimization. More on that in a minute. This approach generally allows facilities to optimize their OPEX, their surcharges, and really improve their overall plant stability. So here in this slide, we show a few subtle differences in the project models. On the left, we show a digester system focused on maximizing biogas output. We can see the feed associated with this type of digester is heavy on the solid content. On the right, however, we show a more typical industrial manufacturing process or processing facility where we won't always have a high solids content, but we will likely have a high dissolved organic content. So here the goal is improving and providing stable pretreatment to meet compliance typically. So here we have a nice simple 30,000 foot overview. Before we jump into the specifics about high rate digestion, it's important to understand why and where these wastewater pretreatment processes are not only suitable but required. So if we take a closer look at the industrial operations, so the industrial pretreatment model, more specifically the food and beverage market, we find that the project drivers are considerably different than the conventional solids biodigester project models. For these industrial applications, the concentration of solids in the primary effluent is considerably less than in other applications. The main goal here for these facilities is to meet local regulations and be under compliance for local POTW discharge. Most industries are focused on staying in compliance, so these industries need a stable, reliable mechanism for wastewater treatment. So here in this slide, we try to highlight at a high level, show an overview comparing the key characteristics of the different digester roles. On the left, again, we see a high solids content, a focus on biogas output, larger retention times, and a focus on revenue and profits. On the right, however, we can see that the industrial pretreatment mentality includes improving treatability, improving stability, ensuring compliance, but we also find that we have lower hydraulic retention times and a higher focus on OPEX, not necessarily creating revenue or making profit. So before we get into the details of anaerobic wastewater pretreatment, let's take a look at where most industrial facilities start. It's really no secret that worldwide there are more aerobic operations than anaerobic, and this is mainly because most of the wastewater out there is low to medium strength. And truthfully, aerobic operations are usually best suited for the large majority of these wastewaters. Conventional aerobic processes have been around since the early 1900s, and there are even more modern aerobic technologies, let's say, that came into the market in the later part of the 1900s or even the early 2000s. Generally speaking, these are recognized as reliable processes, but these processes start to lose their effectiveness and economic viability as the strength of the wastewater increases or as the variability of the wastewater increases. In such cases, the energy demand, the excessive sludge production, and the sensitivity make aerobic operations a poor fit in some of these industrial applications. So here in this slide, we've tried to highlight a few of the most common aerobic processes used in wastewater pretreatment. We've also highlighted a few common rule of thumb associated with aerobic system design, such as your typical organic concentrations you would expect, how much oxygen is required for the organics and the nutrients, and the different type of process efficiencies that we can expect when using different types of aeration. So let's elaborate on those physical limitations of aerobic systems, specifically as the strength of the wastewater increases. So what you find is conventional aerobic systems start to experience a nonlinear escalation in oxygen demand as the organic strength increases. So this is what we see in this slide in series 1 above. This directly increases the energy consumption of the system. Basically, from here, a snowball effect starts to occur. Meeting higher oxygen demand requires more air, longer HRTs, larger systems, larger blowers, and this is demonstrated in series 2 above. As the strength of the wastewater continues to increase, we reach a point where the oxygen transfer efficiency begins to decrease rapidly under higher aeration rates, and this is really due to high bubble velocities and bubble coalescence, as well as reduced contact time and potential mixing limitations, and this is highlighted in series 3 above. As a result, these systems start to reach a practical and physical limitation. There is a point at which your oxygen transfer efficiencies are maximized, your air and energy are wasted after this point, and you generate excessive sludge because of the higher food to microorganism ratios. And this is really captured in series 4 through 7 above. Ultimately, we reach an inflection point where the technical viability, the economic viability of aerobic systems become simply out of reach. And this is precisely when high rate anaerobic pretreatment becomes necessary. So let's elaborate on those physical limitations of aerobic systems, specifically as the strength of the wastewater increases. So what you find is conventional aerobic systems start to experience a nonlinear escalation in oxygen demand as the organic strength increases. So this is what we see in this slide in series 1 above. This directly increases the energy consumption of the system. Basically, from here, a snowball effect starts to occur. Meeting higher oxygen demand requires more air, longer HRTs, larger systems, larger blowers, and this is demonstrated in series 2 above. As the strength of the wastewater continues to increase, we reach a point where the oxygen transfer efficiency begins to decrease rapidly under higher aeration rates, and this is really due to high bubble velocities and bubble coalescence, as well as reduced contact time and potential mixing limitations, and this is highlighted in series 3 above. As a result, these systems start to reach a practical and physical limitation. There is a point at which your oxygen transfer efficiencies are maximized, your air and energy are wasted after this point, and you generate excessive sludge because of the higher food to microorganism ratios. And this is really captured in series 4 through 7 above. Ultimately, we reach an inflection point where the technical viability, the economic viability of aerobic systems become simply out of reach. And this is precisely when high rate anaerobic pretreatment becomes necessary. Now let's talk in more detail about why granular biomass is so important. Granular anaerobic biomass offers several advantages compared to suspended phase systems, mainly because the granules are dense, compact structures that allow for excellent settling. The settling efficiency is what allows for such a high retention and high rate of retention and allows us to grow larger and larger granules. So this retention efficiency and the size of granules prevent washout that normal suspended flock systems may otherwise be subjected to during periods of increased loading or increased hydraulic loading. Second, the layered structure of the granular biomass supports a balance of microbial species, so it allows slower growing organisms a secure growth space on the inside of the granule. In this slide, we show what typical anaerobic granular biomass looks like. Generally speaking, you're going to find granules between 0.5 to 3 millimeter in diameter, and we'll talk about why and how we optimize the size selection in the coming slides. The outer layers of this granular biomass are typically the faster growing microorganisms, while the internal structure allows for a safe space for the slower growing microorganisms to develop. Another defining feature of these high rate granular systems is the internal hydrodynamics of the reactor. So these systems rely on an upflow to create a superficial velocity, and this is mainly to expand the granular bed to promote mass transfer without washing out the granules. From this perspective, the upflow velocity can be controlled by external recirculation, and we'll talk more on this external recirculation in a minute. The result is essentially a fluidized bed where granular biomass and incoming wastewater are in direct constant contact. The upflow velocity and granule densities create a form of hydraulic selection. Basically, lighter granules are pushed up or out of the system, and the heavier, larger granules are retained in suspension and continue to mature. It's not uncommon for the upflow velocity to be modified during startup and into full acclimation. This is basically to balance the formation and the retention of granules as the system acclimates. So let's take a second to pause here. Now that we know the basics, let's recap on the main benefits of these systems before we discuss Fluence's EFC process specifically. So granular anaerobic systems enable very high loading rates, and this enables a compact, low HRT system. These granular systems operate with a fraction of the energy otherwise required in conventional aerobic or even conventional anaerobic systems. The key point is that granular biomass retention is essential to all of these systems. Any high rate granular system must have the proper operational flexibility, that is, the ability to adjust the mixing or account for solids retention to have the best performance. So how is the Fluence EFC high rate process different? Well, we really have three distinct design features in the EFC process. First and foremost, the most important is the fact that we utilize an externally forced circulation system, hence the acronym EFC. Many other high rate systems actually use biogas to aid in the mixing of the granules. This is really to make a claim that you use less external energy or less external mechanical energy by borrowing some of that biogas. We actually aim to decouple our reactor mixing from the biogas production because it allows us to mix independent of the biogas output. So this is a huge advantage for maintaining process stability and maintaining granular retention. In more conventional high-rate granular systems that act as a gas mix system, these systems can experience swings in mixing intensity and internal velocities as the biogas production goes up and down with incoming loading. This can lead to poor granular separation. In other words, a less expanded granular bed with all sizes and densities kind of mixed together inside of the reactor. Now, one may think that this is a good thing, but keep in mind that we're trying to maintain specific, larger, more dense granules in the core of the reactor. So without consistent external mixing, it can essentially lead to stratification within the reactor during periods of low biogas production and lower mixing. By contrast, with an external mix process that relies on controllable liquid mixing, it delivers a more consistent, more controllable reactor velocity, granular velocity, independent of the biogas output. So this results in a more predictable, a more controllable, and a more stable operation for these systems. Okay, second important feature of the EFC process is that we do not require a pre-acidification step. Generally speaking, where our EFC process is applied, there's no risk of having lignin or cellulosic materials, so pre-acidification really makes no sense. Pre-acidification is counterproductive for a lot of these wastewaters that we deal with that are composed primarily of dissolved organics. Basically, it can disrupt the balance of acetogenesis and methanogenesis that granular-based biomass can actually manage within its own internal cell structure. If using a pre-acidification step, what happens is the system can rapidly convert soluble BOD into VFAs, that is volatile fatty acids, and the pH and alkalinity can really take a dive and can actually inhibit downstream methanogenic growth. At the same time, these pre-acidification steps often produce a low quality off gas or low quality biogas. And this biogas is too poor to burn and it has really minimum methane content. So it ends up with its own separate biogas treatment system. The result is a more complex, higher cost system with reduced stability. So the slide here highlights the advantages of bringing wastewater directly to our EFC process, and we eliminate the need for pre-acidification. With the type of wastewaters that we find within the food and beverage industry specifically, pre-acidification is not required and can actually minimize the total usable biogas potential of these systems. So let's take a second to pause here real quick because that last slide contained a lot of information. Basically, to recap on the benefits of going direct to a granular process, we have number one, higher methane yield, i.e. we have no low value biogas to deal with from the pre-acidification step. Number two, greater process stability, i.e. we have less swings in pH and alkalinity if we're not allowing pre-acidification to take place and for VFAs to form. And number three, it's a lower CapEx system. Basically, we're eliminating unnecessary infrastructure. And the final, better performance in simple operations. Now, I had mentioned our secondary solid separation process in a previous slide, so let's take a closer look at this unit. This slide here highlights our external solids recovery step. This is one of the final key factors in our ESC operation. By adding this step, by adding a secondary solids capture unit, we can now prevent biomass decline because we can now enhance our biomass retention, and this helps to stabilize our long-term performance. So the process is designed to capture the smaller finite granules that may escape the EFC process from time to time. And by capturing these granules, we can now loop them back to the EFC and we can allow them to have further contact time and further development. With an integrated loop back to the EFC, we simply improve the total solids retention efficiency. We can achieve a higher organic loading rate without worrying about washout of these finite granules, and we can enhance the resilience to any hydraulic or loading spikes. So the results after having the system incorporated are typically lower final effluent TSS values, higher methane yield consistency in the reactor itself, and the reduced need for seeding. So where do these types of systems excel? Well, these systems are widely applied within the food and beverage processing space, specifically alcohol production, dairy processing, soft drinks, juice production, etc. Basically any wastewater with high soluble COD and low solids on the inlet. Other industries include fermentation industry, the biotech industries, specifically those that are processing yeast or enzymes or amino acids. Pending the scale of the operation, even some pulp and paper industries are also a good fit, specifically those with mill process water or pre-treated water or evaporator condensates. Agro-industrial facilities are also a good fit, particularly those that are processing sugars or starches. And there's nothing quite like having a visual. So this slide actually highlights the many different EFC units in operation around the world, operating across various industrial operations, manufacturing, processing operations. Many of these systems have actually been in operation for well over a decade, so they're very trusted long-term technology. Most of the tanks that you see here require very minimum footprint compared to what an aerobic process would have required, or even other anaerobic systems. And these reactors, these EFC reactors, often have diameters well under 20 feet. So these systems are capable of reducing organic loads by well over 90%. I would say 80 to 90% is kind of the sweet spot, but there are some systems that can achieve higher than 90%. So these are a great method for providing stable, trusted wastewater treatment prior to POTW discharge. And with that, we will conclude our introduction to higher rate digestion and Fluence's EFC process. If you have any questions or interested in discussing further, do not hesitate to reach out to me directly or reach out to any of us at Fluence at any time. I hope you enjoyed the presentation and have a better understanding of how high rate digestion can be applied. Thank you, and I look forward to seeing you again on the next Tech Talk.